picking up good vibrations.
In this video, we'll start with some basic introduction to signals, and we'll talk about transformation of signals, some properties of signals, and finally we end up with a very important signal called the Dirac. Now, signals are nothing more than functions of one or more independent variables. In this course, we'll focus on functions of one variable, namely time. However, for instance, an image, which is a very important signal, is a collection of pixel intensities, which are functions of their horizontal and vertical position, which is not time. It's an example of a signal which does not depend on time, depends on other variables. Now, time can either be continuous, for instance, time as we usually know it. In that case, it belongs to a set that belongs to R, but it can also be discrete. In that case, it belongs to a set that belongs to the integers. We'll denote a continuous time signal, let's say x, with the notation x brackets, round brackets t, and a discrete time signal with the notation x curved brackets n. Now, a signal, let's say my voice signal, typically starts at a given time t1 and ends at a given time t2. However, it is mathematically convenient to define it from the interval from minus infinity until plus infinity. If we still want to model this signal that goes from t1 to t2, we by convention say that it's 0 outside of this interval. There are also signals of interest which are mathematical abstraction, let's take a sine of t, which we can say that it goes from minus infinity until infinity. At this point, there's some mathematical issue here. For instance, how do we distinguish a signal that goes from 0 to 10 from another signal which goes from 0 to 15, but is actually 0 from 10 to 15? To do this mathematically rigorously, we would have to always take with us the domain of the signal, but we're not going to do that, and we're going to sacrifice a little bit the mathematical rigor with respect to simplicity. Now, here are a few examples of signals. We have, for instance, a cosine or a sine that has a given frequency, omega naught, a given phase phi, and a given amplitude, capital A. In discrete time, we can define also this signal in the same exact way. Also have exponentials. In continuous time, they're given by c times e to the power of alpha t. If alpha is larger than 0, the signal blows up as t goes to infinity. If alpha is less than 0, the signal decays and converges to 0 as time goes to infinity. In discrete time, an exponential takes the form c alpha to the power of n, where if alpha is larger than 1, the signal blows up as n goes to infinity, and if alpha is less than 1, the signal decays and converges to 0 as n converges to infinity. We also have cosines multiplied by exponentials, both in continuous and discrete time. This class of signals turns out to be very, very important. Other very important signal is the heaviside function, or the step function. And continuous time is defined as being 0 from minus infinity until t equals 0. At t equals 0 is equal to 1, and then for positive time is also equal to 1. In discrete time, the definition is similar. This is a very important function. Often we will just, if we have a signal that starts at 0, if we multiply by the heaviside function, we immediately have the signal to be guaranteed that the signal is 0 for negative time. For instance, the next function here, the ramp, I can just say that it's t times the heaviside function. Same in discrete time, it's n times the heaviside function. Finally, we have the rectangle, which is 0 outside of a bounded interval from L underline until L bar.